rework on the quantum mechanics exam helped me some, not as much as I wanted it to, but so now I have a 41 out of 65.
That's good. Okay.
So that's in legitimate B range for a curve, though I still have a lot of things that I need to.
Yeah, that's what my understanding is that as far as the grades, probably because what's going on and various situations, I think you should be fine. And, the question is whether you want to are satisfied or
not. I'll be honest, if I got an A in that class, I would feel dirty. A B, I can accept based on the way things are going, but there are, I do understand there are a lot of things that, I look back over my old, like the textbook that my quantum professor used, and things like that. And I don't know that he did not pursue it with the rigor that Dr. Berg does.
Then it's good, right? So that's.
And I think that, since discussing things with Bishari, she thinks that his expectations are legitimate for that level, then I need to kind of bring myself up to that level.
That's right. That's right. I think that's the way to look at it. That always helps.
I do think that the test that he gave for an hour and 45 minutes was, you could not write continuously for an hour and 45 minutes and answer all those questions, let alone ponder.
That will be really fluent with it. You begin and
So even having to go back and forth to the provided material.
Well, you might be able to if he actually taught something in class, but he didn't teach anything.
over again. I would think its volume is low.
Your volume's all.
It's better or it's better?
There it is.
Oh, I was just saying you might be able to actually finish it if he actually taught what you take on tests. He doesn't really teach anything in that class.
Now that test was I worked on it for 12 hours on Sunday to do the rework, and I still couldn't complete it.
That's probably the worst class I've ever taken.
48-hour test that he gave to the class last year, which he did. Moses was saying he would give them 48 hours to work on an exam. And I think that's the exam that he wrote.
Yeah, I mean, it doesn't surprise me at all.
Of course, then I look at things that I had, that I expect my students to do, and it's like they think it's impossible, and I can do it in a minute and a half.
You don't really know where you're at in that class, which is another problem. So you could spend the entire semester studying something completely incorrectly, and you'd never know.
Hello, Alia.
Hello, doctor.
Okay, where is Moses? Always here. Did you guys go for lunch on Sunday?
Yes.
Then, Moses told me, but I missed that. Okay. Okay, I think we're begin maybe. 9 minutes.
I know that Moses was up at like 3 a.m. working and stuff. So,
Okay. Oh.
so he might have.
Yeah, he might have just decided. Okay. Yeah, possible. So, what's going on at 2 p.m.? Is that
I got an
he's
email.
not in quantum, right?
Yeah, no, but I got an email that came through at about 11 after 3. I didn't get it this morning, but he was up working I remember pulling all-nighters when I was young to do that.
Yeah.
It's not done by 10 o'clock now, it's gonna wait.
Yeah. Okay. And for the last homework. Everything has to be due by Friday midnight, right? But beyond that, it doesn't go. Well, that's your wall that you touch. From that point on, then you need special permission from me. And, it gets very hard for it. First of all, there are legal issues that I cannot make anything due beyond that date. And second, it's just convenient to get the bills. Oh, he did make it.
Oh, no, sorry.
I said that you were up late working, so we weren't sure if people.
Oh, yeah.
And I didn't get your email for this morning, so I was not up late working.
I figured you would be.
One more seat.
Upgraded? Did you say upgraded?
Yeah.
I think it is an upgrade.
In a
That's
sense.
my fault.
I have to work a little bit more.
Yeah, it's not a really good seat, right? Oh, yeah, Michael. No. Michael sometimes easily.
I tried to upgrade, the other day when I used it, I tried to upgrade the table there.
Huh?
The residual dry erase marker got so bad, I
Yeah.
took a bunch of the
How do you clean it?
I got some of the disinfecting wipes from the lab.
Oh, okay.
I used to use this, but they ran out.
Okay. Yeah.
And I ran over it with 4 wipes and it came up still completely black.
Because sometimes I use this and it makes it worse. But I just use it all. Okay. Okay. So we have 2 more classes remaining. Today I will, we have developed the radiation field. We have actually derived the radiation field in a formal expression for it for any general current distributions if you want. And today we will do an example which I think is very insightful. It gives you a good insight into how things happen. And then we will be left out with 1 class. Typically what I do is that I do the frequency distribution of the radiation. Now we have the angular distribution. We will also be interested in what frequencies go into a certain angle. Like think of an antenna. If you have a cell phone antenna, of course you want to orient it in a certain direction. At least you have the control on it. But you also want to see what is the frequency dependence. If the source has a lot of, it's like music, and then what directions what goes. And I derive that, and then I do what is called Cherenkov radiation, which uses that frequency dependence. But with the time limitation, I might pick one. I might either write down the frequency expressions and then do the Cherenkov, which is sort of just because Cherenkov is so interesting. But I might also decide to just do the frequency expression because it's much more resourceful in the sense that you have the full expression and you can apply it anywhere you want. So then it's up to you to see. So that's what I might do. We'll see. I haven't decided exactly which one to pick. So that's so you might miss out on something. Okay. So let's recollect. Today what we want to do is we want to do a very simple antenna. We have our expressions. Let's construct a very simple antenna. And whatever I do here will be the simplest version. And in your homework, I will do this for one antenna. You will be two of them. So if you have two antennas, then you can have interference, right? Like you have a double slit experiment. There are certain places you can have interference. So that's what you will do. Mostly it will go through the things that I'm doing on my speeches. So remember, your radiation fields are given in terms of the magnetic field due to a radiation from a source multiplied by C. That's just to get the dimensions like that of an electric field, is minus R hat crossed with. Let me write this as V dot C over 4 pi. Remember, this has the dimensions of resistance. This is the same as mu naught over epsilon naught, square root of that. So the dimensions of resistance. And put in a 1 over R, which is the characteristic of radiation. You pick up the 1 over R potential or 1 over R field. And whatever is remaining has to have the dimensions of current. And I figure out there is a letter called iota, volt. So instead of current, it has some direction associated with it. And this is R hat. And this is T minus R over C. R hat just means that it depends only on the direction. So that means it depends only on angle theta and angle phi. It doesn't depend on the distance R itself. So again, we are, the picture is that you have some distribution of charges or currents or whatever, and that's your R prime, and you're observing it very far away. On a dome, if you pull out the R dependence completely to be of the form 1 over R, so then it becomes a dome out there. 1 over R, it's like looking at the night sky, where all the stars are pretty much at the same distance as far as observation goes. They're all stuck on a dome of the sky. So that's the idea. And here, I think we called this I effective in the last class with the vector sign, which is pretty much what I'm calling I today. So this could be R hat or angle theta phi T minus R over C. This is equal to integral over all the sources. Collect all the sources, and it's the time derivative of the current density. It's R prime and P minus R over C plus R hat dotted with R prime over C. R prime gets integrated out, so it doesn't depend on that. So it only depends on the geometry of whatever is producing the radiation. And T remains, R also remains, but most of the R is collected in this 1 over R potential on the angle. That's the idea. And we notice that if we were to calculate the electric field, it's perpendicular to this magnetic field. And its magnitude is exactly the same as that of the magnetic field. And also these are perpendicular, right? So all three R hat, electric and magnetic field are all perpendicular. So let me also write that C times magnetic field is R hat cross. Again, on the dome that I'm talking edge. We also showed that typically we are interested in the power, not the electric and magnetic field itself. In that case, we said power is energy over time. So the power per unit solid angle we showed is equal to this comes from, remember, flux of energy is E cross H. We derived this last time. And the expression for that can be written as so power. So you should have the units of power. So it has 1 over 4 pi that's for the solid angle, sort of normalizes the solid angle. And power is I square over I square times R, that's the resistance. And the I here comes out as C times B. So this is very general expression, and divide that out by not C over 4 pi, then 1 over R. It's a way of writing it. So remember, if I remove this piece of that, the remaining is the dimension of current. So that's current squared times the resistance is equal to power. Right, and when you look at it in an independent context, so for example, if you were to ask what is mu naught over epsilon naught, when you say this is approximately 30 ohms, right, that's very intriguing, because this has the this seems to suggest that this is some property of the vacuum. That's correct. That the question remains open. But here, in this way of interpreting, here you can say that there are some currents that are producing radiation, and this is a resistance for that current to convert itself into radiation. So not all possible geometries easily radiate. So this is often called radiation resistance. So that's the way you would say. But keep that in mind. But I should clarify that at that time this is not what comes in. So, for example, usually, if you were to write this as let's say, if I were to upgrade this, there's some current I naught square which is inside a wire, and this will be having mu naught C over 4 pi and some geometry of the current. So, for example, if it's a circular current, it might be the radius of that. So there might be some frequency omega naught times A, some function of that, some dimensionless one. This whole thing is called radiation resistance. So it's not just this piece, but this is called radiation resistance. And we'll calculate that for the simple antenna we are talking. So what I mean is that even though this has a resistance, and it becomes interesting very soon, because then it becomes a geometry dependent concept, and you're not really dependent on the details of the quantity. So there are nice things associated with that, but the calculation gets hard. So keep that in mind whenever you're thinking of, because I kept it slightly open earlier that this is you don't know anything about that, but yeah, just think along that line whenever you want to imagine. Okay, so now we want to do a concrete example. We want to calculate. Oh, let me write one more step. One more step. This looks a little overwhelming, so let's make it simple. Right, this is just mu naught C over 4 pi times the way we defined our effective current. This is minus R hat crossed with our iota. I define this iota square. If I know the effective current, cross that with the direction in which you're looking at, that's your radiation. How much power is radiated per unit solid angle is completely determined by that. Okay. So let's do a simple example to illustrate how these things go through. So that's where the simple antenna comes. Simplest antenna, maybe. It should be taken in the spirit of when we talk about a mass sliding on an incline in the first few examples we do in introductory physics. That captures a good bit of physics there, but after all, it's an idealized situation. So similarly, an antenna is very advanced, is very rich. A lot of things have been done in it, but this is the first step. And it's almost like building a bridge and doing introductory physics. So I don't want to give an idea that this is everything more antenna, especially recently with cell phone antennas, they're very good. For example, one would think that cell phone should not work inside a car, right? Like, why shouldn't it work inside a car? It's a metal surrounding, right? It's a Faraday cage. So cell phone shouldn't be working, but they work great. So they work around those features and they made it nicer. But still, Faraday cage is electromagnetic proof. So yeah, Chris, how does a cell phone work when you're inside a Faraday cage? Like if you put your cell phone, like often in a undergraduate physics, you make this proposal that put your cell phone inside a can, a metallic can, and then call your cell phone, you won't be able to get it. But I think at least 2 years back when I checked it, that was true. I mean, you will always say that, oh, there is a small hole here. It's not supposed to go, right? But it rings. So, yeah, let me know if you guys know a simple explanation of these things. Okay. So, yeah, simple antenna. So, what are we talking about? So, we have it's just one wire, one straight wire. That's it, and of length L. So let me align it just one wire, and it will have current. How do you make the current movement? I don't care. Right? It's just one finite wire, and the wire current in it oscillates with some frequency. So let me say, just to put in some coordinates, this is 0, this is your origin. That's your 0, 0 minus L over 2. And that's your 0, 0 plus L over 2. So obviously, as I've shown it, it is aligned with the z-axis. And that's your z-axis if you want. And you would like to see some radiation coming in this direction, R. So that will be my angle theta. And there is a current going through this. So how do I specify that? My J, the current density, would be, so since it's going to be R prime, right? It's going to be integrated out. I begin by writing it as R prime itself. So it's T prime. It's going to be current is in the Z direction. So I'll say this is the Z direction. Its current itself is having a time dependence. So it has an amplitude, I naught, and it's a sinusoidal current, but having no position dependence. At every point, the current is the same. So it's like magically you have a current is 0 in the wire, and then everywhere there's a current going in and then going slow off. More realistic would be that it's called a center-fed antenna, where it is you start from the current here, then slowly it's like a wave. That's more realistic, and that's called a center. So that's called a center-fed antenna. That's more realistic, but this wants a lot of simplicity. There's the position dependence, one factor gone. Okay, so this is not a center-fed. This is simpler than it. The center-fed antenna is one of the simplest antennas. This is simpler than it. So, okay. And this is omega naught T, and since it's T prime, T prime. So the whole wire has the same amount of current at every instant. So this is current. I need current per unit area, right, for current density. So I have to specify the thickness of this wire. It's really infinitely small. So I say this is del f of x prime and del of y prime. It's the thickness of the wire, like current per unit area. Remember, delta function is 1 over length as its dimension. A little more, I have to also specify that this is finite in length, right? So I also say that by our step function, right? So this is supposed to be built out of step functions, but I just say that whenever the argument is satisfied, it is 1, otherwise it is 0. It's a generalized step function. Okay, that's your antenna. Okay, any questions on the construction or geometry. Our goal will be to put this in there and get our power curve. What's the distribution of power around it? That's all. Okay. And we will do some simple situations where now there are two parameters, right? Oh yeah, I should introduce that. So there is omega naught. So it seems like length is the only parameter. This one. But there is one more parameter because there's frequency. Right? So let me define that frequency over the speed of light. That becomes a wavelength, right? So that will be defined as yep. So 2 pi times wavelength. So there are two parameters in the problem: the length of the wire and the wavelength associated with the oscillating current. And then there will be two. So the moment there are two parameters in a problem, you can talk about comparing. What if the length is very large compared to this? What if length is very small compared to this? And there will be two different regimes. And that's what typically radiation, whenever you see that, you will see that in scattering radiation of two parameters, one is the small limit and one is typically also associated with high energy and low energy. And quantum mechanics, every other problem is the moment you have two parameters, you compare with what happens in those two scenarios. Okay, so that's what we have. We need time derivative of this. Not even time derivative. We need to first evaluate this at some weird point, right? At some retarded time. So let's do the retarded time. Move this away. Okay, so let me substitute this at r prime t minus r over c plus r hat dotted with r prime over c. I would like to evaluate this at that point and then take the time derivative. Right? That's the idea. So that's z hat I naught sine of omega naught times substitute the whole thing. But before that, let me see what this r hat dotted with r prime is. R prime as of now is anywhere because I am going to integrate everywhere. But since there are delta functions specifying what my r prime is, constraining my r prime, that's going to be always on the y. It's on the z-axis. R prime is on the z-axis. So this dot will actually pick r hat dotted with r prime. So it brings that cosine theta out and also the z, right? Z prime. Let me write that down and you let me know if there's any confusion. So it's t minus r over c, that's an observation point, plus r prime is z prime over c, and then there is cosine theta. Is that clear? This dot product is just z prime times cosine theta. Any questions there? And that uses the fact that x prime is equal to 0, and that also uses the fact that y prime is equal to 0. And if you allow me to be lazy or not use the second one, not really use lazy or save that space, so I'll just put a theta function. That's just repeating the whole thing. I have to take the time derivative of this. Let's take the time derivative. It's time derivative of j of r prime comma t minus r over c plus r hat r prime over c is equal to time derivative only touches this. So it switch this to cosine, omega naught comes in the front. That's all that is. It doesn't touch anything else. So z prime omega naught I naught cosine omega naught t minus r over c plus z prime over c. Actually divided by C also, right? There's a 1 over C. That definition omega naught over C is also done. And then it involves 3 integrals. Right. I have to integrate over x prime, y prime, and z prime all over the space. X prime and y prime integral is trivial. Right? That's the only place where it's trivial. And z prime integral, even though not trivial, at least the theta function can be removed by putting the limits. So my iota, or the effective current I, or hat E minus R over C is equal to Z hat omega naught over C times I naught. Actually, omega naught over C, we said it was 2 pi. People get cancelled very soon, but we like that. 2 pi omega, sorry, 2 pi, what is it? 2 pi, 2 pi over lambda naught. And then there is I naught. And there is integral minus L over 2 to plus L over 2 z prime, x prime and y prime gone. And this is cosine omega naught t minus R over C plus C prime. Simple. But that integral is doable. Right? And then we have the magnetic field, and then we have to sort of straightforward. Right? So cosine integral is sine, and then we have to evaluate that at z prime equal to plus L by 2 and minus L. Okay, so we'll do that. Any questions at this stage? Okay. Okay, so we have our I, or iota. Iota is equal to z hat I naught 2 pi over lambda naught, and do the integral of cosine is sine, but then it has to be evaluated at plus L over 2 and minus L over 2. So, and then divided by the coefficient of z prime. So first let me get the coefficient in the denominator. So that's omega naught over C, and then cosine theta. Actually, this would have been better if I just replaced it as kept it as it is, so that it will cancel that immediately. And the two quantities are sine of omega naught T minus R over C plus L over 2, right? L over or omega naught over C L over 2. So this is omega naught over close this and plus omega naught over C L over 2 cosine theta. Correct? I think so. And minus of sine omega naught T minus R over C plus 1. sine A plus B. Yeah. Yeah. Okay. So this omega naught over C cancels out. Z hat times I naught, dimension of prioritized curve. That's okay. And there is a 1 over cosine theta. And the numerator is I can expand sine A plus B, right? Sine A cosine B, right? Integral cosine B, sine A. Yeah. So sine A, sine cosine B, and there is this first term cancels out, right? If I were to trigonometrically expand this, let me do this. You have sine of A plus B here, and minus of sine of A minus B. So that's your A, that's your B, and same thing there, right? So this will be sine A cosine B. So this is cosine A sine B, and minus of sine A cosine B plus cosine A. No, this was minus A plus. Right. These to cancel out. That's fine. So there's 2 times cosine. So what we have is this is the same as 2 times cosine of this piece times sine of this piece. So this is 2 times cosine of omega naught times P minus R over C, and sine of this quantity. So this is sine. We'll maybe erase this part. And sine of B is actually omega naught over C is 2 pi over lambda naught. So 2 cancels out. So this is pi L over lambda naught times cosine theta. And this whole thing is divided by cosine theta. That's your effective current that contributes to radiation. That's it. So this is so now let's do power, right? So maybe one more thing. So R hat crossed with I is R hat crossed with Z hat, and whole thing repeated. I naught times Q times cosine omega T minus R over C times sine pi. Okay. R crossed with Z is, if you go back to our diagram, this was your antenna, that's your R, that's your Z. Z hat, R hat, that's your angle theta. If that was an angle theta, then that's R cross Z will be sine, right? And since we are going to be squaring it, we don't care about the. So this is going to give you a sine theta. There is a direction associated with it, but I'm going to square this, so that's not going to constitute. That's so my power per unit solid angle. I'm ready to write that down. Let's go in space. So this is dP by the omega solid angle. Remember, is solid angle is sine theta, d theta, d phi. We need that very quickly. But as of now, that's just solid angle is equal to 1 over 4 pi times mu naught over C by 4 pi times I naught squared. That is the power, right? That's the dimensions of power coming in. I naught squared. And there's a sine square theta. That's coming from R hat crossed with Z hat. And what else should I do? Should I do this 2 Yeah, let's take care of this Q. So that's 4. And that is cosine square omega naught T minus R over C. Sine square of pi L over lambda naught cosine theta over sine square theta. That's your power radiated per unit power. As I mentioned earlier, in your homework, what you will be doing is, we did this for a single wire of length L. You will keep 2 wires exactly of the same length, separated by a distance A. So now you have a new pattern. Right? But then 3 parameters too much, right? So this is L, and then there is lambda naught. Right? So 3 parameters is too much for analysis, and that is for me. So what you can do is, or at least in your homework, what you do is, let's take the limit L tends to infinity. L tends to infinity is not really good, because then it goes too far. Right? So, but we will say that L is very large compared to 1. It's not too big. It is big, but it is very small compared to your dome. Very small compared to your dome, but still it is very large compared to it. So in the leading order, this L effect can be captured in the coefficient. So all the L dependence goes away, and then you have these 2 very long rods that will behave like a double slit experiment. You have this nice radiation, and the pattern that you get exactly comes out to be the double slit. And it will be only the one more thing is that there is this angle theta is no more interesting, because you want to stick yourself to theta small in that plane. All the double slit happens on the plane, right? Of theta equal pi by 2. So that's your homework, but these will be simple stuff. You guys do the hard stuff. Okay. So that's your power per unit solid angle. And you can do one more thing. There is time dependence that is sort of taking away some. So remember, what are the parameters here? There is lambda naught, length, and there is angle, and there's time also too much again, right? We don't want too much parameters. Let's simplify our analysis. That's average over time. Anyway, light usually oscillates very large wavelength, at least for visible light. But this is an antenna, you can actually control it significantly. You can even talk about microwave, right? So it is significantly small, but let's average over time so that we get rid of the time. But that's just simplicity if you want to keep it here. So average, so we have to define the average. So this is a function of time here, P of T. So I'm going to define average power to be equal to integrate over time of any function of time. Right? We are talking about power, but integrate a function of time. And then you go in what, since this is oscillatory, so you go from omega naught, right? So I need a time period associated with it. So omega naught is 2 pi over time period, right? P naught.
Could you bring the camera down some?
Oh, sorry.
No, it's okay.
Yeah. Okay. Okay. Thank you. So we are integrating over time. Average average take care of every time, but since it's oscillatory, you say that I have to also go only from 0 to t, 0 to t naught. So one period, and then this doesn't have the dimensions of power anymore. That's your standard average. Right? This is what, and if you go back to kinematics, the average velocity was having a big issue. Right? That was a problem, challenge. That how does it capture always the instantaneous velocity? So this was there, and intuitive also, right? No issues there. So how does this work? So the only time dependence is here. Right, so that's equal to 1 over T naught. So this is 0 to T naught. So I should put it as T naught is 2 pi over omega naught. 2 pi over omega naught. And dt cosine squared omega naught t minus r over c. But it's squared. If it was a cosine function, average of that is 0. But this is cosine, and that's why it's always talk about power, right? If you were to do electric field average, it would be 0. Right? Moses, didn't satisfy? Drawing. Okay. Okay, so that's cosine squared. If it was cosine function, average is 0. This is cosine squared. This is the standard thing that happens even in noise. Any sort of, when you say vacuum has characteristics, that's exactly the thing that vacuum, when we say is it should be perfectly 0. But then if vacuum is on an average 0, then that's when you come in the properties of vacuum. The electric field might be 0. Average of an electric field might be 0, but the square of the electric field need not be 0. And square of the electric field is what the energy is. So even though electric field on an average is 0, energy need not be 0. So that's the feature. Same idea here. The average does not go to 0. And what is that integral equal to? Cosine square integrated over a time period in your AC circuits. AC circuits. So what's that called? Root mean square, right? Voltage. Isn't there a definition to that? So that depends on this integral. So quiz. This is straightforward.
Like 1/2. Or...
1/2. Yeah, very good. So you use that double angle formula. You write this as 1. So cosine squared is 1. This will be dt 1 plus cosine of 2 omega naught bracket. But this is a complete cosine, averages to 0, the factor of 2. So this comes out to be exactly half. Half. Yeah, that's it. If this was what did it do? Yeah, half of the coefficient. Right now I need the dimension. So this is equal to P naught, right? And some function of f of t. Otherwise, I don't get the dimension. Okay. Get on with that. What should I do? F of t. Let me just say this is some function. If that function is cosine square, then it's dimensionless complete. Then I can. Is that clear? I did not want to put power because then I'll have to put P naught here and I want to define P naught separately. It's just
There's still a 1 over T naught, right?
no, because T naught cancels this.
Oh, okay.
Right, there's a dimensional cancel. It will work out.
Yeah,
Because here you will go from 0 to T naught, right?
yeah.
So 1 over 2 times T naught, and there is a 1 over T naught here. Okay. So that will go away. So it's factor. Did I confuse? Okay, work it out. So we have, let's define the T average in the board space. Yes, so I'm averaging out. So this is average power per unit solid angle then is equal to, let me define this whole piece here. It is still in the board space as P naught. Okay, that's captures your coefficient of power. So that's P naught over 4 pi. And then we have pretty much there's a factor of 2, cancels one of this 2 times sine squared. That's much simpler to deal with. What does it depend on? Only 2 parameters, right? It depends on angle, theta, and it depends on L over lambda naught. That's it. This antenna has only 2 characteristics. It's angle dependent, and it depends on the ratio of the length over the wavelength, or wavelength means how you're oscillating the current. That's it. Rest everything, the coefficient depends. It's the intensity. Okay, clear?
Are you still missing a sine squared term?
Oh, yeah. It's thank you, thank you. So let me write it here. It should be the boundary. That's correct. Thank you very much. That's 2 times sine square pi L over lambda naught times cosine theta divided by cosine square. That's it. And we will do 2 scenarios now. So and that's again, one should appreciate that this has only 2 parameters. In fact, if I talk about the total power, then it has only 1 parameter, right? L over lambda naught. If I don't worry about the solid angle dependency. We'll talk about two extreme scenarios, 1 and 2. One is when L is very much less than lambda naught. It's pretty much makes really tiny, small piece of wire. It depends on lambda naught, of course. If you don't really have to make it tiny with respect to our hands, it is with respect to lambda naught. If your frequency is large, then wavelength goes down. So that's relative to that. That is true. And the second we will do is when the length is very large, extremely large. And typically, this will be a low energy, this will be a high energy. So those are the ways to look at it. So this is low energy, high energy. Yeah. Yes, please.
So you, like it seems like you could write it in terms of tangent squared of theta, but is there a reason that this structure is?
Yeah, because when I start integrating, it is good to keep working. Notice, I can immediately motivate that. For small angles, very small angles, L over lambda naught is small. Then sine function is just the angle itself. So cosine theta code cancels out immediately. So just to see that I want to write. Yeah, good one. Yeah, that is a reason. So, and in your homework, you will see that when the length, so in the other limit, it is equivalent to putting sine theta equal to 1. I motivate that in your homework and probably will also. So in one limit, this whole thing becomes cosine theta cancellation and this becomes 1. So there's a good reason to keep it separate. Yeah, good question. Okay, so let's proceed. So let's do the simpler situation. Usually low energy is usually simpler. Quantum mechanics, we would say this is the what's that? Which Oppenheimer approximation. I think that's what it's called. Born Oppenheimer approximation. That's what it's called. And it doesn't any low energy approximation. It's so if you have a series, if you're taking the first couple of terms, that's low energy. If you're interested in the last couple of terms, that's high energy. And both have simplicity often. Right? It's easy to capture both. Typically, not necessarily always, typically easy to capture both sides. In between is the hard one, very hard. Extremely hard. So, L over lambda dot, so we will do the simpler situations, right? So in this case, L over lambda naught times pi times cosine theta. Cosine theta doesn't go more than 1. So this is approximately, pi, no, what did I say? Sine of this is approximately pi L over lambda naught cosine theta. Right? Because even if cosine theta, whatever you take, that's actually small. Which means that sine theta divided by cosine theta is just this pi over naught. And my power per unit solid angle is simple, naught 4 pi sine square theta factor of 2. And then this is simple pi times L over lambda square. Everything else. Now this in principle should be combined with that resistance, and that will become your new resistance. So resistance depends on the geometry of the antenna, so that becomes a real radiation resistance. If you like, that's straightforward at this point. Any questions here? You're not satisfied here?
Yeah.
You're fine.
Oh no, I think I'm.
What's the concern?
Yeah, I was thinking, I was skeptical because you go from, like, you have a sine squared and you're saying that each sine is like simplifies to this, like you're taking a first order approximation of both sine
Yeah,
terms.
inside this there is no approximation, right? I think because
Yeah,
this
so,
is the approximation.
so
It's not a sine function.
I was skeptical because it, like, to say that, like, you have a first order approximation of the sine function, and when you say that, then when you square that to say that, like, the sine squared function
Oh.
is second order, but I think it's okay because sine's not a function, so you don't
That's-
have first.
That's
Okay.
the leading order. Yeah, good question. That should I be keeping the square term here to capture this? But this is a coefficient. The first term is okay. Yeah, good, good thought. Yeah, good concern. Yeah. Okay, so that's and at this stage, this can I think this should be written as best way to write this is 1 over 4 pi times, remember I naught square is there, right? So let me capture your sine square theta here right away. 4 pi is for the d omega normalization. Whatever is remaining should be written as I naught square times R, which is resistance, which is mu naught C over 4 pi, times whatever is remaining. So this is Q times pi L over lambda naught square. And this you will define as the new resistance if you want. So this is your radiation resistance or radiation. I don't know what it's called. That's mu naught C over 4 pi times Q times pi L over lambda naught square. So the resistance depends on the length of the antenna in the small antenna approximation. So that's read this, but let me keep that whole expression there. I'm interested in just that we will do the opposite approximation very soon. We have time to think. But before we do that, let's quickly, once we have this is an easy integral to do. Okay? Let's do the complete power, total power emitted by this antenna. P bar, average total power emitted by the antenna, is integrate over the omega, complete dome, right? And 1 over 4 pi over 4 pi sine square theta. And that whole coefficient is unnecessary, right? This is just yeah. This integral is straightforward. The phi integral gives you 2 pi. That's 2 pi over 4 pi. Then that is 0 to pi sine theta d theta. And 1 minus the sine square theta, easier to write this as 1 minus the sine square theta. And this is just constant, I don't know. So the angle dependence does not have. So substitute cosine theta is equal to t. That gives you sine theta. D theta is equal to dt and minus sine. So this is 1 by 2 minus. So this is at 0 cosine theta is plus 1 minus 1 dt minus dt. 1 minus t squared t naught 2 times.
Can you lower the camera again?
Being bad. You almost missed 2-3 lines. Sorry.
No, that's okay. I'm caught up.
Yeah, feel free to say it anytime. You should. Don't hesitate to. Sorry. Okay. So this integral is your, so this basically switches the power. Then there is 1 minus t squared. These are both even functions. So it basically this whole integral is quite quantity. So that's 1 minus 1 over 3, and then you multiply by 2 because of the 2 limits. So it is 2 by 3. That's 4 by 3. 4 by 3, yeah, normal form. Right? Same. So the 4 by 3, 2 cancels out. So this is P naught 4 by 3. And again, one should remember that this goes into your radiation resistance. So resistance depends on the length square. But we will see that will be an interesting thing that's going to happen in the opposite limit. This will actually lose a power. It depends on the geometry. And those are the things usually becomes harder to visualize or has more conceptual implications when the power of something changes in some limits. But as of now, this is just dependent on the square of it, and one can argue that it is because how much energy is getting radiated in a certain angle. Okay, so any questions at this stage? So that should give you a simple insight of what's going on. But now we want to do the opposite limit, where length is very much large compared to the weight. Okay. And actually, I should also point out, so notice in this case, there is a simplicity in this whole point that so you have a wire here, and you're looking at the, so this is your very magnified version of it. So that's your angle theta. And you're looking for radiation because of this sine square theta. What is happening in here is that it's pretty much the radiation is decided by sine square theta. And theta is equal to pi by 2. Here there is a lot of radiation, right? At theta equal to 0, there is no radiation. If you construct such an antenna and you have a cell phone here, you have no signal. Very good signal there, and low signal here. And if I were to plot that, so so typically if you use a polar plot to do this, you would say this is your it's 0. So the length of the vector, if you remember in polar plot, decides what you're plotting. Another way to plot this is that this be my reference, and it is sine theta. This is your 1, this is your 0. Is that clear? So it's more signal there, it's 0 signal here. But this is not what is typically used. You use polar plot to plot antenna. If you look into antenna books, they always plot polar plots. It is a nice thing. Then you talk about lobes, 1 lobe, 2 lobes. Here there is only 1 lobe in the sense it goes to 0 when it is pi by 2, and your signal goes maximum, minimum. 0, maximum, minimum, and the same thing on the other side. There is only 1 lobe. So clear, and the lobe will become clearer when we talk about the next time, where this will become very narrow. Okay. So with this,
that's for a small antenna.
this is for the small antenna. Yes, this is small antenna. So I've drawn the big versus small antenna. Is that Okay?
Yeah.
Is that bothering conceptually? So small means even though I draw this, I didn't tell you what lambda is. This lambda might be here. As far as it's small, at least 50% accuracy. And that. Okay. What's bothering you, Jordan?
Doesn't in this case L have to be less than lambda in the picture that you drew on the right?
Yes, yes, yes. Here it's all L is very much small compared to lambda. So maybe if you're worried, let's make this small. Okay. So lambda naught is somewhere here. That's lambda. So that's about 5 times smaller. So 20% accuracy. 20% that's 0. 20% accuracy. Is that your problem? Helps? Okay, yeah, okay. Now let's go to the other approximation. This is the harder one. So let's do lambda naught. And then also it can take more time, right? But it's Tuesday. So go back to the same idea, right? But now we cannot make that approximation, that the angle inside sine is not a great approximation. So we have to do the following approximation now. So what we'll do is let's substitute first of all. Yeah. So as I mentioned earlier, this is that's our observation point, right? That's your R, that's your L, and that's your angle theta. And apparently our radiation is mostly concentrated here, right, in the perpendicular plane. In this case, it's not, I'm telling you in the later that this is having more radiation. So it's a good idea to have this as a reference. So you'll first do a very trivial change. Let's have things in terms of that angle chi instead of this theta. Then what we can do is chi goes from negative to positive somewhere. So the idea is that first let's ask sine of pi L over lambda naught times the sine theta. Where does it go to 0? So earlier case, it started from maximum and it actually doesn't even have to have gone. They actually said that it goes to 0 here, but it goes to 0 because of the sine square theta term, not because of the this sine function. But this itself could go to 0. Like somewhere here it might go to 0, and that's how your interference. If you remember your interference formula, that has this feature there, right? If you remember, this is the what is that called? Wave number. What's that called? Wave. Like interference formula has this feature that if you were to do this, right? So that is this wave, and then from that wave. If these are coherent waves, subtract out, and whatever is remaining, the difference is what matters, right? You subtract out 2 waves and whatever is the path difference. What is it called? And you can capture this. So this is the measure of these 2 differences. Always, that's how it comes out. But we don't have to worry about that.
So it's equal when your theta value is equal to the cosine inverse of that.
Exactly. Exactly. Or, so we can ask when is this 0, right? And this will be 0 whenever this is n times pi. This will be 0 whenever it is n times pi. Did I use n anywhere else? No. Right? Where n is equal to 0, 1, 2, and so on, right? And plus or minus. Correct. So if I start with the first one, let's start with the first one, n is equal to 1. N is equal to 0 is trivial. So n equal to 1 is what you were trying to say, Jordan.
So that's theta is equal to pi cancels out the sine inverse of lambda naught over L. And this is somewhere, if it is less than pi by 2, then we have minimum. So it will be, if n was equal to 0, this will be cosine theta is 0, that will be pi by 2, right? So this will be slightly less than pi by 2. That's what we want to do. That's where the pi helps because the linear subtracted from pi by 2. So we'll substitute pi. So this is what we want to keep. As you increase n, there might be multiple rows. Right? This is that is by n. So this could be n. For each n, that is, if I were to now plot this again, right? So there is a maxima here, then it might go to 0, and again go to 0. It's fine. Plot like this up. That's it. That's and if you were to do a polar plot, this will look like loads. So this is the, when it goes to, every time it goes to 0, it gets pulled in. So there's a lot of radiation in this sector, and again, a little bit, but this is over amplified. So this way, you get a better picture of it. But this is what is more popular, and this is neat. So radiation goes into some regions more than the other. And the question then comes, that natural question is, how much radiation goes into this, right? If it is going to be only, if it is reasonably equally distributed, then it's not very interesting. But what we'll see is that for a long antenna, this could be as high as 90%, usually about 90%. So if you construct a simple antenna, only those who are perpendicular to that are going to get it. So it's not a very good design for a cell phone, right? Unless you build different ones for this one. Okay, so that's with that all perspective. Let's actually now write down this and try to evaluate how much power goes into that. And I said I'll do some approximations, right? So let's substitute with the idea of yeah. So first, let me substitute theta is equal to pi by 2 minus pi. This is having the geometry in mind. I want that as the reference. Immediately, d theta becomes minus d pi. And what else happens? Then we have the limits, right? We have cosine theta. Wherever I see a cosine theta, this switches to sine of pi, and sine theta becomes cosine of pi. Those are changes that happens, and my power per unit solid angle now. So the average power per unit solid angle is equal to, where is my formula? That's P naught over 4 pi. And I should be careful here also. This is now usually sine theta d theta. So now this is cosine pi times d theta is minus d pi. Right? And d phi, there is no d phi. Let me just put it. Is that okay? Is that clear? What I did there? So P naught times 4 pi, and then sine square theta becomes cosine square pi. And I have 2, and I have sine square pi L over lambda naught. Cosine of theta is sine pi. And this is sine square pi. I think that's what I'm doing. Let's see. That's good. And yeah, so we are interested in eventually integrating, right? But we are also interested in pattern, what happens. So in these cases, the good substitution typically is to get this whole thing as z. Let's substitute z, the tilde actually. Oh, that's my, yeah, let's keep it z. I like it to call it z tilde because it's dimensionless. So that's just, let's substitute that. Then we have dz now is equal to pi times L over lambda naught times cosine of pi times d of pi. Great. And there is this minus sign. I'll take it to the right hand side. So, or let me leave it as it is because it's a solid angle that's in there. Keep it as it is. So this is dp average power, and here I have notice d cosine of pi times d pi is dz. So this dz. How did I write this? Minus is there anyway. 2 pi dz. And then pi times L over lambda naught goes to the numerator. It's better to write it on the right hand side. I don't know where I'm keeping it on the left hand side. But it gives you the idea that that's all part of solid angle. This P naught over 4 pi. Cosine square of pi is 1 minus sine square of pi. So it is 1 minus sine square of pi is z square over pi times L over lambda naught square. And then there is 2 sine square of z divided by z square, z square over pi times L over lambda naught square. That's also exist in the denominator, pi L over lambda naught. Denominator of the denominator. Okay, that's all that is said. Okay, good. Okay. That's all algebra. But now remember, our length is very much larger than lambda naught. That means L over lambda naught is very much larger. It's almost infinite. L over lambda naught is infinity as far as we are concerned in that approximation. So this is very large. So this can be constant. And that's the approximation. But basically, this was sine square. This originated from this whole thing was sine square theta, going back to the question that was provided. So this was basically sine square theta. And in your homework, you will see this. Wherever, instead of doing it at this stage, we will analyze sine square theta separately, because there sine square theta appears in a lot more places. So wherever you see a sine square theta, you're allowed to make it 1. That's the way you will motivate it in the homework, because it will have this construction. Okay, so, but one more cancellation. Notice that's the dimension coming in. So this cancels this. Oh, so the average power becomes proportional, linear to the length of the antenna instead of the square. So let me write this as dp or over dz times 2 pi. The minus sign is equal to actually 2 pi and 4 pi cancels out, right? Factor of 2, that cancels out, 2 cancels out then. So this is simply minus dz. So we have p naught times sine square of more. So this, when it goes, this is already the denominator of denominator. When it comes up, it's down here. And that is sine square z over z square. That's it. That's your angle dependence if you want, but that's given in terms of this construed parameter z. But let's actually we can do a few things. If we want to talk about what's the total power, that's an easier one. The total power will be doing the complete integral. That's minus dz. And where does z go from? Am I within the? No. So in the approximation that we have made, my phi goes from minus pi by 2 to plus pi by 2. So z actually goes from where to where? So z goes from pi sine of minus pi by 2 is minus 1 to plus 1, but L over lambda naught is pretty much infinity, right? Minus infinity to plus infinity. So if you are doing total power, so that's just minus infinity to plus infinity, and you have sine square z over z square. Now that's a nice integral. If there was sufficient time, it is good to evaluate this. First of all, remember, if you recall, in your complex analysis, there is a nice integral that you work out. It is sine of z over z. This has, notice sine of z over z, naively speaking, is 0 over 0, right? It starts behaving crazy, right? But then in the z tends to 0, it is really nice limit. So this integral is nice, and one should like try to, yeah, look great. I'll encourage you guys to evaluate that integral. It can be very nicely done using complex analysis, and it turns out that this minus infinity to plus infinity z sine square z nicely gets converted to just by integration by parts. If you do integration by parts, you can convert that into that. So it is 2 times 0 to infinity z sine z. Very nice. Basically, this is the nice part, but since this is connected to this, that's all. So if you're interested in these kind of integrals, then that's kind of a neat results there. So that's pi. So you get total power is equal to pi. But that's p times pi naught over pi over lambda naught. Right. So that's a total power. But one might be interested in asking, oh, I'm not interested in this. I don't want to go from minus infinity to plus infinity. I'm interested only in that first lobe. Like we talked about lobes there. How much is just the power radiated in that tiny lobe? And in that case, you don't want to go from all the way from minus infinity to plus infinity. So let's call this. So this is usually, at least in your textbook, this is written as one lobe, right? First lobe. So then just the limits has to change. So this is minus, instead of going minus infinity, you go, chi goes to this, right? You have this, the sine inverse of this, which will become sine inverse. So you basically go from lambda L lambda naught. So you go from L over lambda naught to minus L over lambda naught plus. And then you do z. And then, oh, so you've already done the z integral actually. This comes out just 1. This is just minus 1 to plus 1 because of the way we did it. So this is just minus 1 to plus 1. So this is the integral that you get if you're interested in only in the first loop. Again, it's just a few steps. It's the limits minus infinity to plus infinity becomes -1 to +1. And that integral is hard to do. Right? You cannot exactly do that, but again, there are nice ways of doing it. You can make a series, you can build series expansions for that, or you can do numerically. But however you do that, this comes out to be about approximately 0.9, which tells you that it's 90% of the radiation goes into that. I did not thoroughly go into the last part, but that's okay to a certain extent. And yeah, I think in your homework also you stop at this stage or somewhere here, and then yeah, no, in your homework you don't do this. What do you do in your homework? In your homework, actually, yeah, you do take the limit L tends to infinity, and then you start working with. Yeah, you have more terms actually because that's an interference limit. So that's not the line of thought. But I think it's clear. Hopefully, asking questions. Yeah, sorry about that hand waving argument at the end, but you guys feel it anytime. Next time we'll cover the rest, whatever I can. Yeah. Any comments or questions? What is useful?
Yeah, I'm a little confused about the negative infinity to infinity part.
Oh,
Just
okay.
changing when you went through the process of changing your variables.
Oh, let's do that. So I can do that. Yes.
Stated that theta was equal to x.
Yeah, I think the negative.
Minus pi over 2. Yeah.
Yeah, let me do that. So this was, we substituted theta was pi/2 minus pi, correct? And then z was substituted to pi L over lambda naught times sine of pi. Agree? And theta was going from 0 to pi. Agree? And so if theta was going from 0 to pi, right? 0 to pi. So that means chi will go from when theta is 0, chi is pi/2. Right? So this is pi/2. And this goes when theta is equal to pi, it is pi/2 minus pi, so it's minus pi. Okay, so it goes in the opposite direction. Instead of going from minus pi/2 to plus pi/2, it's going from pi/2 to minus pi/2. Clear with me till now?
Yes.
And z then goes from, right, when chi is equal to minus pi/2, this is -1. So this is less than minus pi L over lambda naught. And this is plus pi L over lambda naught. Good. And L over lambda naught we agreed was infinity. So this is going to minus infinity, and this is going to plus infinity. And actually that helps me because I think there's a problem in this expression that I wrote. So the negative sign in front, right? That's not good. And that's exactly this negative sign. So that negative sign flips this order of limits. So there is no, if you allow me to change that. Yeah, so this should be plus, right? Then I sort of hand wave it. So that's true. So your question helps me to fix that. Did I answer your question, Jordan? From here, minus pi/2, I came here. And then I said L is very large. So that's basically infinity.
Yeah.
So Z goes from minus infinity to plus. Or plus infinity to minus infinity. Was that your question? It's still bothered.
Just for some reason, like I see what you're doing, but not sure what I don't know how to formulate my thoughts.
concern.
Something feels weird. I'm not
Something
sure.
feels weird. Okay, weird or you think
Yeah.
we missed?
Um,
Like I think this whole idea is just to capture this. Like this is the angle theta. This is the phi, and I have an approximation where phi is small. What are the quantities important?
It's weird to me that we keep the factor of pi at all over lambda naught.
Phi,
Yeah, like it, yeah, just, yeah, that, yeah. The,
we have to, right? Because we cannot drop numbers,
right, no, yeah.
or it is weird, you're saying, or it's new in a sense, right?
Well, in the limit that's really large.
Phi is not large, right?
No, but all over lambda naught is large.
Oh, why you keep this? Oh,
Yeah.
I see. Oh, this is infinite. Why do you keep this? Because that's a coefficient. Yeah, I mean, good point. So if you remember, all your radiation formulas, like it is large, but it's not really infinite.
Yeah.
But that's the best you can do, because if you take it to infinity, everything goes away. And if you take it to the denominator on the left hand side of the building, you don't have a choice. So it's a leading order characteristic. So for example, it's like saying, if you have a series f of x where x is very small, if it starts with x, you don't have a choice. You
Yeah,
stick with it, right? It's only relative to something, it's always large or small. So here there is no relation. This is the scale of the problem itself.
I get, yeah, it makes sense.
If it's a coefficient, you cannot cover.
Yeah.
The next term is comparatively small. It's always with respect to one, right? With respect to one, it is large, or small. So yeah, I see the point.
But then our average power for the first load would be like 90%
Of
of that coefficient.
So it's okay. Yeah, but it's very, I mean, that's why, I mean, taking the limit L tends to infinity completely is not the right way to say it. It is large. And always when you do this infinite limits, that's what we are having in mind. And actually, good point. Like for example, here there is a scale, right? The moment you have a scale, you have a physics associated with it. You're safe. And sometimes, very rarely, there are situations where there is no scale. And then if you say that something is infinity, you are in trouble. And that's what happens in electrodynamics, quantum electrodynamics. That's exactly what happens. There is just one constant that is basically the charge of the electron. And something is an infinity. So you don't have these arguments with it. So there it is a real infinity. And you're in trouble. But here these things are better because physics says.
Yeah.
Okay, that's 20 minutes crossed. So thank you for allowing me this extra time. Jordan, did I answer your question? Oh, sorry.
Yeah, I was just thinking,
Yeah.
you know, the benefit of just doing it by symmetry. So you just maybe do the top half. Because when you do the integral from like 0 to infinity, use that, you know, sine squared over sine squared z over z squared equal to sine of 2u over, or sine of 2u over.
The substitution.
So you can say pi over 2.
Yes,
You could say the integral is equal to pi over 2.
that's correct. Yeah,
Times 2, so you get pi.
that's correct. That's exactly correct. Yeah. So I just hand waved it, but you're seeing that correct. You're actually seeing that substitution. Very good. Yeah.
Yeah, but I didn't do that. I just said that that will be equal to that. But I thought, I think the main points I have remarked, so hopefully you can fill in the steps. I didn't do those things. Yeah, good point. Yeah.
Okay.
So I jumped. Yeah.
Okay.
I usually don't like to do it, but then I was thinking time in that. But then anyway, we are spending 20 minutes discussing that. I could have just
No, I just,
done it and there would have been no questions. Yeah.
okay. Alrighty. Well, thank you.
Yeah. Yeah.
Goodbye.
Sorry, yeah. I think, okay. Yeah. Fill in the steps. I want a quiz. Another quiz. Too many quizzes today, but yeah, you guys know I'm fine. Thanks, Alia.
Thank you.
Good luck with the, and some homework related questions, if that's okay.
Sure.